So in this series of videos, we are going to understand how transformers understand natural language. Consider a given sentence. So how will transformer differentiate? The sentence is talking about animal was tired or street was tired. For us humans, understanding sentences like this is almost instinctive. But for a deep neural network, it requires a powerful mathematical mechanism called self attention. Now you must be asking what self attention exactly does. Imagine reading a sentence and for every word you briefly look at all the other words to understand its meaning. So that's exactly what self attention does. Before we go further into the video, I want you to understand what vector embeddings are. We know that neural networks cannot directly understand text, so we convert the text into n-dimensional numerical representations called vector embeddings. There are two main types of vector embeddings: static embeddings and contextual or dynamic embeddings. Now, let's understand how static and dynamic embeddings differ from each other. Consider the given sentence. Are both bank in the sentence same? The answer is no. Although the word is identical, its meaning varies depending on the context in which it appears. Let's look at how both embeddings encode the given sentence. So if you use static embeddings to encode the given sentence, it will encode both financial and river bank as same vector. While on the other hand, contextual embedding encode bank as different vector, cause both bank are used in different context. This awareness of context makes dynamic embedding special, and modern large language models like GPT to use contextual embeddings instead of static embeddings. You can pause the video and read this. Now we are going to see how we can convert a natural language sentence like I, like math, and convert it into contextual embedding using self-attention mechanism. Before directly jumping into self-attention, we have to pre-process the input text. So we convert the given input sentence into tokens, and this is called tokenization. Tokens are fundamental units of words, but a token is not same as word. A token can be a word or part of word or even a symbol. But here, in this case, we can clearly see there are three tokens. After tokenization, we find the static embedding of each token in the sentence. Here, E1, E2 and E3 are static embeddings of those three tokens. For this video, we assume dimension of each embedding vector is D or D model, and we combine each vector to form a embedding matrix X. Hence, size of embedding matrix is 3 times D. Now, let's build a quick intuition for Q, K, V or query, key and value. To generate contextual embeddings, we transform each vector embedding into three representations: query, key, and value. Query, it means what a word wants to find in other words. It helps decide which ones to focus on. Key, it represents what a word contains. So other words can decide whether to pay attention to it. And the dot product of query and key measures how similar or relevant two words are, which is then used to decide attention score. Here in the give matrix, each row represents a query vector for each token and each column represents key vector for each token. The values in the matrix are the attention scores. The higher the attention score, more influence a token can have to decide other token. Let's have a look at first row. So the contextual embedding of I is mostly influenced by I itself and then by the token like and at last the token math. We can take same intuition for other rows as well. Now let's understand what values are in Q, K, V. So far we have decided who to focus as shown in the matrix. Now values represent the information of each token. The final contextual embedding is the product of attention score and value vector. This was the quick understanding of QKV. Now let's look at math part of attention mechanism. This is the embedding matrix X, whose each row E1, E2 and E3 represents static embedding of the tokens. I like math. Now we are going to take weight matrices WQ, WK and WV. These matrices are the learnable parameters or weights whose values are decided during backpropagation. Here I have taken size of each matrix as D model times D model, but you can take other size as well. Now we are going to perform matrix multiplication of embedding matrix X with weight matrix WQ to get a new matrix Q of size 3 times D model. Similarly, we multiply X with other weights matrices WK and WV to obtain K and V matrix. Now let's take look at what is stored in each row of Q, K and V matrices in this query matrix. Each row in the matrix represents the query vector of given tokens. So first row represents query vector of token I. Second row represents the query vector of token like, and third row of token math. And for key matrix as well, each row is a key vector of each token. And same is true for the value matrix also. So let's take Q and K matrices. Previously we have discussed that we need to find dot product of query and key vectors. So we transpose K so that each query vector can be dotted with every key vector at once using matrix multiplication, and the resultant matrix obtained after Q times K transpose is attention score matrix. So after we have got attention score matrix, we have to scale down the matrix by root k, where k is dimension of key vector. But for this video we have taken dimension of each vector as d model, so we scale down the attention matrix by root d model and obtain scaled attention scores. Now it's time to pass scaled attention score through softmax function. Softmax is a popular activation function used in deep learning, and on the screen you can see the softmax function. Now we will apply softmax function in each row in the matrix. You can see that each row sums up to 1 due to softmax activation. These are called attention weights. The final process of attention mechanism is to multiply attention weights with value vector. Here we have value matrix. So the end result of this multiplication gives us output matrix whose each row represents the contextual embedding of the given tokens. Here first row is contextual embedding of token I, second is of token like, and third is of token math. Now each embedding obtained are context aware and are ready to use. Thanks for watching the video.